we're looking at a position time graph. The position time graph, in this case, represents the motion of a basketball coach during the last 16 seconds of overtime during the past weekend's game. So all of the questions right here can be answered by looking at this position time graph. But first, I'm going to tell you what a position time graph is showing you. So the x-axis on the graph is time in seconds, and it goes from 0 seconds to 16 seconds. The y-axis is position in meters, and it goes from 0 meters to 8 meters. The red line is representing the basketball coach's motion, and it's representing how far he goes and how fast he goes. So, the first question is asking you to determine the total distance walked by the coach during these 16 seconds. Well, to find that, you just add up all the movement in the y-axis. So you look here, 0 to 8, so that's 8. Then he stays still, and he goes 4 meters, that's 4. Stays still, goes 4 meters, 4, and then he goes down 8 meters. So you just had to add up 8 plus 4 plus 4 plus 4, and you get a total distance of 24 meters. Now, it doesn't matter what direction he goes, because you notice sometimes the slope is going up and sometimes it's down, but it's really just the absolute value of the distance, whether it's down or up, doesn't matter when you're talking about total distance. So I went 24 meters. Resulting displacement after 16 seconds is the next thing you have to determine. Displacement is different from distance because displacement is asking how far away from the original starting point did the coach end up. Well, in this case, you can look at the y value, and you see that he started at 0, and over here he actually ended at 0 too. So in real life, this would be like a coach who started at a certain spot, he walked around, and then ended up in the same spot. So to find displacement, you do the final y value minus the initial y value, and in that case that's 0 minus 0, so you get a resulting displacement of 0 meters. So he just ended up in the same spot he began in. Now C is asking you to determine the displacement of the coach after 12 seconds. So right here you have 12 seconds, and you can see at 12 he is 6 meters away. And he once again started at the 0 position. So in this case, you take the y value at 12 seconds, which is 6, and you take the y value at 0 seconds, which is still 0, and 6 minus 0 equals 6. So displacement after 12 seconds is 6 meters. To find the greatest displacement, you just have to look for the highest y value. So you can see that right here, it touches the the 8 value on the y-axis multiple times. First, it touches it from a period of 4 seconds to 6 seconds, and it touches the 8 meter mark again at 14 seconds. So you can really just figure that out by looking at it, but the highest y values are from 4 to 6 and at 14, so that's the answer. 4 to 6 and 14. To find the fastest velocity, you have to look at the slope of each section of the coach's movement. To do this, to find the slope, you have to use the formula slope equals y2 minus y1 divided by x2 minus x1. So it's pretty obvious when you're just looking at the graph. You can see, oh, well, this is the steepest, that's the fastest time. But I just went through all of the math just to check my work, and I'll just start with the first section. From 0 to 4 seconds starts at 0, 0 and 4, 8, and then you take the y2 minus y1 and you get 8 minus 0, and you take the x2 minus x1 and you get 4 minus 0. Divide those two values and you get 2 meters per second. And then I just did that from all the other sections. So I did it from 4 to 6, 6 to 8, 8 to 10, and so on. And I found out that he is moving fastest from the period of 14 to 16 seconds. He's going at a rate of 4 meters per second. And so the fastest velocity would be 4 meters per second. Now the average speed is found by the equation distance over time. Well, we already found distance up here in part A, and time is right here on the x-axis, 16 seconds. So 24 divided by 16 is 1.5 meters per second, and that's the average speed of the coach. And that's the answer to the problem.